In this video, we'll solve the one-dimensional Dirac-Combe potential. We'll first review Bloch functions, then introduce the Dirac-Combe, and then solve it, and finally make the connection between the Dirac-Combe and band theory. So, our task is to solve a system of n identical potentials with the periodic spacing of A, and the potential periodicity is described as V of x plus A is equal to V of x. So what we did is we defined the displacement operator, d, so that if you apply d to a function x, f of x, you get f of x plus A. Since the displacement operator and the Hamiltonian commuted, it was possible to define common eigenfunctions of the two called Bloch functions. That is, they're eigenfunctions of d and eigenfunctions of the Hamiltonian, whatever that Hamiltonian would be. And this results in a potential, in a wave function that is periodic. That is, psi of x plus A is equal to psi of x times some phase factor e to the iqa. So what that means is that when you have a particular function in this period, then it would be the same function in this period, just moved over, but with a phase factor. So Bloch functions, these are Bloch functions, and Bloch functions solve periodic potentials when periodic boundary conditions are imposed, that is, you make the solid infinite. That results in quantization because now if you have n cells and you use periodic boundary conditions, then when you move that potential or that wave function over by n, it will be back to its original state without a phase factor. And so that tells you that when you apply it n times, you get n phase factors multiplied together, and that has to be equal to 1. So that leads to quantization of Q, which is going to be equal to 2 pi over capital NA times n, where n is 0, 1, plus or minus 1, plus or minus 2, and so on. So the first problem that we can solve easily is the Dirac-Combe problem. We're going to use the Bloch theorem and periodic boundary conditions and solve the potential over a single unit from 0 to A, for example, to get the solution for a period, for a periodic lattice of n of them. So our boundary conditions are periodic, that is psi of x is equal to psi of x plus NA. That's e to the I n, capital N, QA times psi of x. That's the periodic boundary condition. That implies quantization of Q, as we showed just before, 2 pi lowercase n over capital NA, where lowercase n is 0, plus or minus 1, plus or minus 2, and so on. The potential that we're interested in is the potential over all n, which is just a sum. So it's V of x is the sum from j equals 0 to n minus 1 of the strength of the potential alpha times a delta function, Dirac delta function, x minus ja, where alpha, as I said, is the strength, and capital N is the number of repeating periods that we have. In the region from 0 to A, we have the Schrödinger equation is very simple. There's no potential there because it's 0, and the boundaries are delta functions. So E psi is equal to minus h bar squared over 2m d squared psi dx squared. If we define the usual wave number k is equal to 2m e square root over h bar, we get a simplified equation, which is d squared psi dx squared is equal to minus k squared psi. Well, we know how to solve that. It's a combination of sines and cosines. So in the range from 0 to A, psi of x is equal to A times sine of kx plus b of times cosine of kx. Now we also want to look in order to apply the boundary conditions, we have to look at the unit just before the origin. That is, the unit from x equal minus a to 0. In that point, because this is a Bloch function, we can write what the solution is. We move back by 1. So we have e to the minus iqa is equal to a times sine of k times x plus a plus b of cosine k times x plus a, where x is minus a to 0. So when x is minus a, this is simply 0. And when x is 0, this goes to a. Right? Because that's basically the function that we had before, but in terms of a shifted position. So we can apply the continuity equation at x equals 0, which says that since the sign goes away, you're going to get b is equal to, again, the sign goes away, e to the minus iqa, pardon me, not sign goes away, a times sine of ka plus b times cosine of ka. So you have both terms in the cell just below 0. And you also have a discontinuity in the derivative. So if we take the derivative here and we apply it at the origin minus the derivative of this applied at the origin, we should have a discontinuity that relates to the strength of the delta function. So for that we have k times a, and x is equal to 0, minus e to the minus iqa, k times a cosine ka, the sine becomes a cosine, and the cosine becomes a minus sine, so it's minus b sine of ka. And that's equal to b, the value of the function at the origin, times 2m alpha over h bar squared. We can now rearrange this continuity equation, solving for a times sine of ka. So a times sine of ka is b times e to the iqa minus cosine of ka. If we divide by sine of ka and substitute the value for a, capital A, into this equation here, the second equation, and cancel the b's, we get the following. We get k times the quantity e to the iqa minus cosine of ka over sine of ka. That's from this term. Then we have minus e to the minus iqa times k times the quantity e to the iqa minus cosine of ka over sine of ka. That's just this term here. And that's all times cosine of ka. And then you have e to the plus, because you have two minus signs, e to the minus iqa k times the sine of ka. And that's equal to 2m alpha over h bar squared. We've canceled the b's, which appeared in every term. So that's where we are with the solution. We can now multiply times 1 over k times the sine ka over k, basically. If we multiply by sine ka over k, this just becomes one term here. And you'll notice it's this term has the same combination, but it has a prefactor of e to the minus iqa. So that first term gives me a 1 minus e to the iqa cosine ka times what was in the numerator up here, which is e to the iqa minus cosine of ka. Then we have this term. When we multiply times sine ka over k, the k cancels, but you get a sine squared. So you have e to the minus iqa sine squared of ka. And over here, you're going to get, on the other side, 2m alpha over h bar squared k times sine of ka. Well, we can do, expand these terms here. We get e to the iqa for the first term. Then we get minus cosine ka for the second term. Then we have cosine minus cosine Ka because these two exponentials cancel. The product is 1. And then we have this term here, which is plus e to the minus iqa cosine squared of Ka. We then have this term, which is e to the minus iqa sine squared of Ka. And then on the right side, we have what we had before, which is 2m alpha over h bar squared k sine of Ka. Well, clearly, these two terms have the same prefactor. Cosine squared plus sine squared is equal to 1. So we get e to the minus iqa. We have e to the iqa minus 2 cosine Ka plus e to the minus iqa is equal to 2m alpha over h bar squared k sine of Ka. We can now combine these two terms to get 2 cosine of Qa minus 2 cosine of Ka is equal to 2m alpha over h bar squared k sine of Ka. So this is a transcendental equation that we need to solve. We can now make the usual substitution. Z is equal to Ka. And we're going to replace this with beta. So we have cosine of Qa equals cosine of Ka minus m alpha over h bar squared k sine of Ka. I've canceled the 2's. Now I'm going to do the replacement. Z is equal to Ka and beta is equal to m alpha a over h bar squared. We get cosine of Qa is equal to cosine of Z plus beta times sine Z over Z. So this is the transcendental equation in simplified form that we can solve. We'll call that f of Z. So f of Z, which is cosine, has to be equal to this quantity here. Now let's take a look at this. The part on the right in red is going to be plotted in red. The part on the left here is a function that can vary between 1 and minus 1. And we're going to plot it in black. If we now plot the red function, we see that it's an oscillation that decays as you go out in Z. As you go out to Z equals infinity, this will be limited by cosine of Z. This term will go away. This term will be the limiting term. So at the end, at Z very, very large, this is just going to be cosine of Z. So it's going to oscillate between 1 and minus 1. The cosine Qa on the other side is bounded by plus and minus 1 always. And so the only time you get a solution is when these two are equal. And that's within these gray bands. So since cosine of Qa, absolute value of that, is less than or equal to 1, the shaded regions, these bands, contain the only valid solutions. And the valid solutions then have gaps between them. These gaps are forbidden energies whose values of K, because K is related to Z, are not allowed. Since Q is equal to 2 pi n over capital NA, it's quantized because of the n, and K, which is a function of the energy, are also quantized. Right? So K, which is Z over A, is related to the energy of the system. And this is the momentum or the wave number of the system in the solid, which is different than this wave number for a free particle. So there are n allowed states in each band. Each state can take 2 electrons if these are electrons in the band. But the energies are very nearly continuous because n is very large. N could be 10 to the 10th or 10 to the 20th. So these are very, very closely spaced levels. Right, in this direction, 10 to the 20th. Imagine 10 to the 20th in this direction here between plus and minus 1 for cosine of Qa. So it's helpful to visualize these bands as a function of Q. So right now we have a Z and f of Z, so we know what the solutions look like. But it'd be useful to see the energy as a function of Q. Now, let's look at this one more time. K is the wave number of the free particle. In the solid, that wave number is modified. It's no longer k, it's q. It has a different behavior. And that's what we're going to look at now. So the solution, as we recall, is cosine of qa equals cosine of ka plus beta sine ka over ka. Q is equal to 2 pi n over capital Na. K is equal to square root of 2me over h bar. And beta is m alpha a over h bar squared. If I set all the constants to 1, we're going to simplify this equation quite a bit, and I can plot it more easily. Now remember that the expression is valid only when the right side is between -1 and +1. So when I do that, I get cosine of q equals cosine of square root of 2e plus sine of square root of 2e over square root of 2e. So now I can plot, when I get values of q, I can calculate e and then plot them. I get a plot that looks like this. So we have a band, and then a gap, and then another band, and a gap, and another band, and a gap, and another band. Now notice we've plotted these between 0 or minus pi and plus pi. But n goes to infinity. So what we're doing is we're taking bands that would be appearing in regions like from plus pi to 2 pi and minus pi to minus 2 pi, and we're transporting them all back into this region from minus pi to pi because cosine of qa is periodic. So we can bring it all back into this and visualize the bands. All right, we can use these bands now to explain properties of metals, semiconductors, and insulators in a very simple way. So, as we said before, there are 2n closely spaced states along the q-axis in bands, 2n for electrons, separated by gaps in energy when there are no available states. The lowest lying states in blue, that I've shown in blue, are much more localized in energy. Their energy spread is very small compared to the bands that are higher up in energy. If a material, a real material, not of delta function, but if you have a real solid like copper in one-dimensional lattice, has an even number of electrons per atom, then the topmost band fills up because there are 2n states, there are n atoms. You fill up all the states below the Fermi energy, and the Fermi energy lies in the middle of a gap. So at this point, you have no conduction. This is an insulator. And the reason it's an insulator is actually a little bit more subtle than you might think. It's because when you apply an electric field to an electron that has a momentum q of 0, you would expect it to move and have a momentum that's a higher value. Because if you apply the electric field in the negative direction, then the electron would want to start accelerating in the positive direction. The problem is that there's no available states for that electron to be in a value other than 0. Because the band is filled, no conduction is possible. If a material is made up of atoms which have an odd number of electrons, then the topmost band is going to be half filled with electrons. Now, this can give a metal. So, in this case, if I apply my electric field in the negative direction, momentum will be in the positive direction. This whole green band here, this green filled band, will shift a little bit this way. So you'll lose a few states in this direction. You'll gain a few states, electrons filled in this state. But now the entire band is moving, or all the conduction electrons are now moving with a particular momentum. So we can explain insulators and semiconductors with the Fermi energy in the gap, and metals with the Fermi energy in the middle of a band.